Have you ever wondered why a bridge suddenly gives way or why your phone screen shatters from a simple drop? Well, it turns out pretty much everything around us, from massive buildings to microscopic components, is in a constant, invisible battle against forces that are trying to tear it apart. We're about to pull back the curtain on this hidden world of stress, strain, and the incredible science behind why things.
Okay, I know that sounds like the beginning of a really strange joke, but I promise you there is a fascinating and really important connection here. Just think about it for a second. A tiny implant in your jaw, a massive bridge, and a layer of coal buried deep in the earth. What on earth could possibly link them?
And there it is, that's the key. Every single one of them is getting absolutely hammered by incredible forces. Pushing, pulling, twisting, that are constantly testing their limits. You've got the grinding pressure of your jaw on that implant, the violent shock waves of an earthquake hitting a bridge. It's all about stress.
Now here's where things get really cool. Scientists aren't just looking at the aftermath anymore, trying to figure out what went wrong. Nope. They're using these incredibly advanced tools to become spectators to destruction itself, to watch that precise, split-second moment when a material finally gives up.
So why does all this matter? Well, because if you can understand the exact physics of how something breaks, you can literally reverse engineer it so it doesn't. This isn't just some academic exercise. This research is the foundation for, well, everything. From safer buildings and more reliable pipelines to medical implants that are actually built to last.
All right, so in this explainer, we're going to break down the science of breaking. First, we'll look at the universal struggle of materials under pressure. Then, we'll learn the specific language scientists use to talk about failure. After that, we'll watch a tiny crack get born, see what environmental forces help it grow, and finally find out how we can actually engineer for resilience.
Okay, first up, materials under pressure. It's easy to just think of stuff like concrete and steel, but I want you to picture, say, a piece of wood, a metal gear, and even a human bone. They couldn't seem more different, right? But deep down, they're all fighting the exact same battle.
And what's really mind-blowing is that the same fundamental physics applies to all of them. The principles that decide when a chunk of sandstone gives way under miles of rock are the same ones that apply to an advanced metal alloy in a jet engine, or even that super delicate connection between a bone and a dental implant. It really is a universal struggle.
So we know everything is under stress, but how do things actually fail? Let's jump into section 2, the language of failure. Because it turns out breaking isn't just one thing. Materials fail in very different ways, and scientists have a whole vocabulary to describe what's happening.
First, you've got what's called brittle failure. And let me tell you, this is the one that keeps engineers up at night. It is sudden, it is catastrophic, and it happens with almost zero warning. One moment, you have a solid piece of granite or a glass window, and the next, it's just gone. In pieces. There's no time to react, and that's what makes it so dangerous.
On the complete flip side, you have ductile failure. Think about bending a paperclip back and forth. Long before it snaps, it stretches, it thins out, it gets all warped. The material is essentially screaming at you that it's in trouble. And this is a much safer way for something to fail, because it gives you a warning.
And this just puts them right next to each other, so you can see the difference. Brittle failure is like glass shattering. It's sudden, it's clean, and it's over in a flash, absorbing very little energy. Ductile failure is more like pulling a piece of taffy apart. It stretches and deforms, and it absorbs a ton of energy before it finally gives away.
But of course, it gets even more complicated. Even inside a single type of material, this here is gang cement, which is a mix of waste rock and cement they use in mines, failure isn't just one thing. It can snap in at least 5 different ways, from one single clean crack to a total collapse. And understanding these different modes is absolutely critical for predicting how something is going to behave.
Okay, so materials can fail in all these different ways. But how does a huge failure actually begin? Well, let's move on to section 3, because it almost always starts with something incredibly small, a tiny, almost insignificant flaw that grows into a crack.
So a fracture basically has a 4-step life. First, a little microcrack gets started, usually at some point of high stress. Then it starts to grow, to propagate through the material. The next step is where things get really dangerous. Nearby cracks start to link up, they coalesce, and form a much bigger fracture. And finally, you hit that point of no return, final failure.
And the science here is just amazing. Researchers have actually watched how as a main crack grows, it can spawn these tiny secondary cracks at its tips, sometimes called wing-shaped cracks. It's this incredibly intricate, almost fractal-like dance that leads to the final break. It's like watching a destructive little ballet happening at a microscopic level.
So, we know how cracks are born and how they grow, but what's pushing them along? What's feeding them? That brings us to section 4. See, a material rarely just sits in a perfect lab. In the real world, the environment itself is a massive, relentless source of stress.
I mean, just look at how punishing the world can be. Think about a simple concrete sidewalk. Over just one winter, the simple act of water freezing and thawing in its tiny pores slowly degrades it, creating microcracks that just get bigger and bigger. Or a sudden temperature change on granite. Even constant low-level vibrations from traffic can slowly, silently damage a bridge. And of course, a single earthquake can weaken a building in a matter of seconds.
So, with all these forces constantly at work, it might seem like failure is just inevitable. But what if we could fight back? What if failure wasn't a bug, but a feature we could actually design around? Well, that brings us to our last section, engineering for resilience. The goal isn't to avoid stress, it's to master it.
And here's the crucial idea. We can completely transform how materials fail. Just look at this. Regular concrete, as we know, fails in a brittle, sudden way. But by adding something like liquid silicone rubber, engineers can completely rewrite its story. It becomes ductile, it deforms, it stretches, it gives you a clear warning before it breaks. It becomes tougher, safer, and way more predictable.
And you can see these applications everywhere, making our world so much safer. This science lets us design bone implants that perfectly distribute force so they don't overload the jaw. It lets us create pipelines that won't just catastrophically burst. And it helps us build railway tracks that can handle the constant, punishing vibration of trains, day in and day out.
I think this quote just perfectly captures the whole point of this field. It's not some morbid fascination with destruction. It's actually a deeply optimistic science. It's all about creating things that are stronger, more reliable, and ultimately safer for every single one of us. It's about turning those endings into brand new beginnings.
Which, of course, leaves us with one last big thought to chew on. We've gotten incredibly good at predicting and controlling how and when things break. We can make them fail safely, we can make them last longer, but is the next great challenge even possible? Can we use all this knowledge to design something that truly defies failure, something that could last forever? What would a world without breaking even look like?